All right, asynchronous class for LP4. So the last LP that we'll be talking about, especially on the concepts. So concepts for in terms of learning outcomes, I get again reactions and mechanisms. So you can use the cheat sheets, both you cheat. There is a cheat sheet for nomenclature and there is a cheat sheet for our reactions and mechanism. So this one is for um, uh, they call this concepts. So I think the last thing that we discussed was about the about the strains. The strains of having a cycloalkane. Having a cycloalkane, and then we knew that there is somewhat a pattern. I've already explained this graph to you. So again, this is the energy with respect to how many carbons are there in an how many carbons are there in a there's a diagram between strain. So strain is somewhat stress, meaning there's force on the molecule, and then with respect to ring sizes, meaning the number of carbons on your cyclo. So that's what it means. So there is a pattern. So I think the next discussion would be how come that patterns happens. So it somewhat explains this one, the trend that we can see for your cycloalkanes. So a cycloalkanes, it's a compound, an alkane that is a ring. So cycloalkanes are somewhat different from your benzene rings, the aryl group. Okay, so we've already talked about those strains, and then this is discussion of it. So there's a conformation of cycloalkane. And then the first one is propane that is with 3 carbons, as you can see. This is not really that stable. Why? Because those strains are higher. So this part here explains why. So again, since it is far from the 109.5, therefore first you have a higher strain angle, angle strain, and then you would have a what you call the other strains. First is really your angle strain, and then your torsional strain. Of course, for that to contort, going back to that 109.5, there is a torsional strain. While for steric strain, this talks about the groupings on which is attached. This is usually important in cases like the cis-trans isomerism, wherein or probably you have a cis isomer. We can see that cis isomer has higher energy, higher steric strain with respect to trans. Why? Because they are located at the same somewhat place. Okay, so that's the best thing that I can apply. I can explain with steric strain, meaning how big a molecule there is, meaning and then they must be in contact, or they must be near with each other. So the more it is near, because again atoms are just protons and electrons, the more it is has a bigger steric strain. So and then you have that discussion of an eclipse. See, because of course eclipse would be with higher energy. So anyway, you can read those. It has energy with it. Anyway, my concern is just you have to understand these things. You really have to read. And then the next one is cyclobutane. So somehow explains as it becomes bigger actually. Those strains become smaller, as you can see on the discussion, because it can really contort more because of the chains that are bigger. So it's not restricted between bonds and of course your all those strains. Okay, now you have to read, and then your cyclopentane is not also so common. So the more strain there is, the more a compound is not stable, of course, because if you will have a higher energy, so if you'll be settling down, you'll be settling down to a lower energy. So the fact that it has higher strain, it has a higher energy, so it cannot settle more compared to those with lower strains. So that's what it means. Pero pareho ikaw, kung karoon ni mon pahuway, makato ka talagang pahuway. Pero kung itim papahuwayan, medyo mari nga sa lagihap, diri ka ito. Amo diri ka stable. Amo gihap ito hira. Di ba? Madagmit nga analogy nira. But of course, there are case-to-case basis. Kay pagka dito duruda ko nga molecule. But anyway, case-to-case basis kay pagka di man ko na cyclohexane, um, this is really the reason why cyclohexane occurs more than the those cyclo which has higher how about C7, C8, C9. Cyclohexane really has lower stress or strains, combination of those strains. While up to C13, of course, there are higher strain. And this is substitute cycloalkanes are the most common cycloalkanes. See that they are common. Why? Because they are less strained. Less strained. So if they are less strained, the more they are stable and occur widely in nature. A large number of compounds, including steroids and many. So steroids are somewhat lipids. So it's one of the biomolecular compound and many pharmaceutical agents. So we're talking about medicine or anything that interacts with our cell. So if it is inside us, bioactive compounds, the fact that they are active, meaning it interacts with our system or the system of those living things. Okay, so those are pharmaceutical agents have cyclohexane rings. The flavoring agent, even the menthol, those cool to our taste, has actually a cyclohexane rings with it. So this is your menthol. This is a cyclohexane with an alcohol, so that would be a cyclohexanol. If I could name this one, that would be an isopropyl. So this could be two isopropyl, and then you have 2, 3, 4, 5 methyl, uh, 2 isopropyl, 5 methyl cyclohexanol. So that's your menthol really. So the common name is menthol, but again, with our IUPAC names or scientific names, it is called 2 isopropyl, 5 methyl cyclohexanol. Cyclohexanol is a strain free. See, it has somewhat don't have strain because it has zero on the strain scale. A three-dimensional shape that is called a chair conformation. Actually, it contours to a chair form of a six sides because of its similarity to a lounge chair with a back seat and a footrest. So this is what it looks like. So it looks like actually a chair. Does it? Some drawings actually look. It looks. As you can see here, going there, you have the seat, and then you have the somewhat um, emo in where you can rest. Yeah, but it is called chair conformation. The easiest is to visualize the hexagonal is to build a molecular model, two-dimensional drawings like that 4.7. So again, this is two-dimensional in a three-dimension fashion so that we can imagine the three-dimension. Chair conformation cycling can be drawn in 3 steps. Anyway, it's a instruction how to draw it. Anyway. I guess by looking at it, we can copy those drawings. We're not kid anymore. In addition to the chair conformation of cyclics and an alternative called the twist boat. So some scientists called it the chair conformation, while other also called it the twist boat. It is a boat which is twisted. Okay, it's somewhat a boat. The one side is twisted. So it's called the twist boat conformation. It's also nearly free of angle strain. So another way of drawing it actually. This is a somewhat a boat, a twisted boat. So, but anyway, this is a conformation, meaning since the angle can, since single bond can really rotate with each other. So again, from chapter 3, we've talked about conformation, meaning it's somewhat an isomer, meaning if that molecule twists in another fashion from one type of molecule, then it is another type of molecule probably, then you can say it's an isomer. Because the definition of an isomer is it's not an identical molecule, but it has the same atoms that is contained. So that's why it is called chair conformation or a twist boat conformation. And then you have the discussion of an axial and equatorial bonds in cyclohexane. So really, that cyclohexane is being explained. How come that from the graph it has a zero strain? So because if we if you know how that happened, then a lot of information can be taken from it and apply it to a probably different compound. The chair conformation cyclohexane leads to many consequences. For instance, anyway, 11.9, we'll not be talking about that. Our only concern as we close the organic chemistry is just um, nomenclature and reaction mechanisms. In addition, we see that simple carbohydrates as glucose adapt a conformation. So most of your sugars actually have this conformation because stable sugars are imminent with six. You have the glucose and the fructose. Of course, the fructose is the sugar from your fruits, and most of your fruits actually contain that fructose, even honey. And of course, sucrose, which is the disaccharide of fructose, I think, and galactose, or maybe glucose and galactose. I just can't remember. But anyway, the lactose, the disaccharides, is just a double, a double six ring. Okay, somewhat double six rings. In addition, and there's a glucose. Then it is being it's being explained what does it mean by axial and equatorial positions. Meaning on the chair conformation, when you have an axis, it's usually talking about this elements or atoms here. Those elements that's usually drawn at the top are called in a axial position. So this is where the cis and trans comes in with discussion, because those that are on the upper side are called axial positions, and those at the on the equator, we call it equatorial positions. Actually, when they are drawn in a two-dimensional fashion, the upper group anyway, it looks like this. Those pinks are like this, meaning they are in three of which are drawn on the top and three of which are drawn down. And then the equatorial positions, they are drawn from left to right, while those other two are being slanted down. So we have to at least be familiarized with it, because that's how they talk about anything that happens to these kinds of molecule. Who bonds with who, or probably who interacts with who. So it would be talking about those equatorial atoms, or probably those axial atoms. So those are their terms. And then of course, since this is just a ball and stick, so you can imagine this is actually more of a how really it looks like if we can zoom them in, because actually they're not, but this one is the last one is easier to visualize than this one, but this is the more accurate. Why? Because they are just ball of energies, and they are really they're just boundaries of energies. So how it is drawn in this fashion, the what they call this, the in terms of um, electron localization, or electron distribution, electron density. Yes. So this is the model for electron density, meaning those that makes the balls are electrons. So you can just imagine those electrons really covering the whole molecule. So that's how it is drawn on apps. We cannot enforce this one because we don't have computers. So we just have to be familiarized with it. Of course, next years will come. Um, you have to be familiarized with how it is modeled in an application, or being simulated by an application. So we are being taught how axial bands and equatorial bands actually are being drawn, because they are really important under discussion, of course. When you talk about, let's say, sugars, or probably other compounds which has this conformation, then um, there are discussions about ring flip. As you can see, the eggshell and the eggshell eggshell and the equatorial is being flipped. So you have the ring flip actually. So it's just being flipped. But anyway, I guess it's already time, so may I cut so that you would have shorter videos.